So basically, there's just a couple quick things from chapter 10 that just looking at the way the multiple choice questions are structured, I just want to reiterate that have kind of been covered in the lesson notes already, but I just want to reiterate them. Also, they've been covered in the POGL. But consider, for example, this statement from the POGL on metal alloys. The interstitial alloy would be more rigid than pure metal because the atoms in the interstitial spaces of the crystal lattice will hinder the movement of planes of atoms when the metal is bent. Okay, so interstitial alloys increase rigidity by hindering the movement of the other atoms, of the larger atoms. So if an alloy is more rigid and brittle, then the atoms are more resistant to sliding past each other. This is one aspect of alloys and their structure that I think several of the multiple choice questions I've seen for Unit 2 that have been asked in the past have talked about. And so I just think it's something to focus on and make sure you understand that connection. That if the atoms slide past each other more easily, it's more malleable. And if they slide past each other with more difficulty, then the alloy is more rigid. And interstitial alloys, by increasing the amount of the interstitial atoms, is more rigid. So in general, interstitial alloys are more rigid, and the higher the percent of the smaller atom, which is often going to be carbon, if we're talking about steel, for example, the more rigid it's going to be. And so you can picture, right, if I'm trying to move these two, well, now this is blocking that. Whereas like here, in a more substitutional pattern, you can imagine they can kind of switch places and kind of squeeze past each other more easily, whereas the interstitial is going to make it more tight. And so, like, also just consider in daily life the functionality of that. So, not as I'm talking right now. Well, yeah, as I'm talking right now, and as I wrote this, like in front of me, there's an aluminum alloy MacBook. Okay, so here's the MacBook. It's not what I'm looking at, but I also use it. And then I have the bread knife isn't in front of me, but that's probably a steel bread knife. But if you notice, if you took a knife from the side, right, you can typically bend it like a bread knife, a long bread knife. It has some give to it. It's like maybe 1% carbon. And then I have my wedding ring, right? And this is an alloy which contains carbon in it, but that could be like 10% or maybe even 15%. Maybe as low as 5, but probably like 10, 15% carbon. Okay, so that makes it a lot stiffer and more brittle, so there's less give to it, and it's also really, really hard to scratch, okay, which is kind of the point. You don't want a material for a wedding ring that's going to scratch. That way it basically stays the same the entire time you have it, okay? So different, whereas if you're using building materials, right, like having just a little bit of give, for example, in the alloy of a MacBook is actually probably good. Like as stiff as this is, it's just a little bit of give. That's probably good, right? If this is in the back of your car, you don't want your keyboard to shatter in half because it has no give and something, right, really, really hard with a lot of force hits it, right? That little bit of give might actually help it. So, anyways, so visualizations of material. That gets into a little bit of physics. I'm not sure how much give versus less give is going to actually increase or decrease the chance it breaks, and that gets into mechanical engineering and a bunch of stuff I don't know. So if it was more rigid, would it be less likely to break or more? But the point is understanding that if they move past each other, that's essentially less rigid, more malleable, and interstitial alloys make that harder. Okay, and then there's a lot of questions that basically test your visualization of solid structures. So just keep in mind, metallic solids are a sea of electrons. Know the difference in what they look like between substitutional and interstitial alloys. Recognize that network covalent solids are covalently bonded as opposed to molecular solids, which are not. It's intermolecular forces keeping them together. And then these are all things we've said, but I'm just saying being able to like recognize visually what it should look like is really important because AP Chem likes to assess that. and know the structure of ionic solids with the cations and surrounding anions and anions surrounding cations. Basically that the pluses and negatives interchange, right? So you should know that like in a diagram, a metallic solid can be represented something like this, okay? And those pluses do not represent protons. In this case, the pluses represent the nuclei of the atom or the metal atom itself, basically, and then the one electron or the electrons given off that are moving around it. Okay, so it represents the atom, which has a positive charge. It doesn't represent one proton or something like that. Okay? And then if we see something like this, we should recognize on the left here, we have a covalent network solid. We can tell because all the atoms are covalently bonded to each other. And on the right, you can see distinct molecules that aren't even necessarily touching. And so that is a molecular solid, so that's different. So again, we should know what they look like visually. I'm just emphasizing that, so you'll see questions like that. And if you miss those questions, you should come back to this brief explanation or the other previous notes on chapter 10. And then if you see an ionic solid, again, whether it's a simple ionic solid with no polyatomic ions or whether there's polyatomic ions, the structure is essentially the same. The positives are surrounded by negatives and the negatives are surrounded by the positives. And it could be depicted also like that image on the right. So you should be familiar with these depictions. That is all as far as miscellaneous from chapter 10. Basically, it's stuff we've talked about before, but know that if the atoms have a harder time moving past one another, it's less malleable, more rigid, and then be able to have some sort of visualization in your head. Make sure you do for what these different things look like, because you will get multiple choice questions probably about that.